Are we having fun yet? Well, of course we are, because we're talking about the hydrogen atom. In our last video, we talked about the solution to the Schrodinger equation for the hydrogen atom. In this video, we continue with that discussion by taking a deeper look at the wave function itself. We start, of course, with just a very quick review of the solution to the Schrodinger equation. We have a wave function that depends on r, theta, and phi, and we separate that into two components. The spherical harmonics, of course, which we discussed in our analysis of three-dimensional rotational motion, and, of course, a new radial component, which depends on the distance of the electron from the nucleus. In these solutions, we get three quantum numbers, n, l, and m sub l, and we'll note that the energy depends only on the quantum number n. It does not depend on L, it does not depend on m sub L, which may seem a little counterintuitive because you learned in general chemistry that the 2s orbital, where L is equal to 0, is lower in energy than the 2p orbital, where L is equal to 1. We'll talk about why that was the situation in those many electron systems in a later video. The quantum numbers n, l, and m sub l actually then represent the angular momentum, where L is used to determine the total angular momentum of the electron, and m sub l is used to determine the angular momentum of the electron with respect to the z-axis. Now, here we take a look at the radial component of the wave function, which is the part of the wave function that depends on r. We're plotting the wave function versus distance r of the electron from the nucleus in this situation. And we see, for example, the 1s orbital, which corresponds to n equal 1, l equal to 0. What's notable about this is that the maximum corresponds to r equal to 0 here, which is at the nucleus. Looking at the 2s orbital, we'll notice that here, where n is equal to 2, l is equal to 0, again the maximum is at the nucleus. And looking at the 3s orbital, we also have a maximum at the nucleus. Looking at the 2p orbital, we note that n equals 2, l equals 1, that at the nucleus, we see that the radial component of the wave function is actually equal to 0, meaning that there's 0 probability of finding the electron there. Then we have a maximum at some distance from the nucleus, indicated here. And of course, if we look at the 3p orbital, we'll note the same thing. The 3p orbital has a maximum at some distance other than the nucleus, as does the 3d orbital have a maximum at some distance other than the nucleus. In this slide, we look at the square modulus of the wave function, which simply means that we're looking at the probability density as a function of r. This would give us a probability of finding an electron at a particular point, and let me emphasize that word point, we'll come back to that a little bit later on, at some distance from the nucleus. No surprises here. These are certainly plots that you would anticipate based on what we illustrated on the previous slide. One thing I want to note is that there are nodes in some of these radial components. In the case of the 2s orbital, you'll notice there is a node here, and a node corresponds to a point where the wave function is equal to 0, meaning there's 0 probability of finding the wave function there. We have one node for the 2s orbital. If we look at the 3s orbital, we'll note that we have two nodes. We have 0 nodes for the 1s orbital. We have 0 nodes for the 2p orbital. Okay. But for the 3p orbital, we have one node. And then for the 3d orbital, we have 0 nodes. So there is actually a pattern. If we look at this, we will find that the number of radial nodes is determined by the n quantum number and the l quantum number, which we represent by this simple equation here, n minus l minus 1. So for example, when we had the 1s orbital with n equal to 1 and L equal to 0, n minus L minus 1 was 1 minus 0 minus 1, so the 1s orbital has 0 nodes. On the other hand, if we look at the 2s orbital with n equal to 2, L equal to 0, we would note that n minus L minus 1 in this case was equal to 1, so we have 1 node, which is perfectly consistent with what we observed on the previous slide. Now, in addition to radial nodes, we also talk about angular nodes. Angular nodes correspond to specific angles where the wave function is equal to 0, and the number of angular nodes will be equal to L. Let's look at that, particularly if we look at the shapes of the orbitals, and these are based, of course, on the spherical harmonics of the wave function. And we'll note that we have the familiar orbitals here. For example, we have the p orbital associated right here. Here is the, over here on this side, the 2py orbital represented here. And you can see there is an angular node right here, right through the center, where the wave function is equal to 0. Now, one question that would naturally arise when we talk about orbitals and these orbital shapes is, if we go back and look at the radial components of the wave function, we note that there was an asymptotic approach to 0, but it never actually reached 0. So how can we draw these orbitals which have finite boundaries? Well, the reality is that what we draw these images, we have what are called 90% boundary surfaces, and that means we simply indicate these boundaries which correspond to a region. They bound a region within which there's a 90% probability of finding the electron. So it's not 100%. So when we look at, again, the p orbital here, this shape does not represent 100% probability of finding the electron within the lobes, but actually 90% probability of finding electrons within those lobes. All right. Now, you may recall earlier that we talked about the radial component of the wave function. When we squared it, represented the probability of finding the electron at a particular point, and we noted that for the s orbitals in particular, that probability was a maximum at the nucleus. This is somewhat deceptive because we're talking about a point in space. When you look at a sphere, and let me actually kind of just draw a circle here. If you look at a circle and you would calculate the probability of a particular point, we'd actually say be calculating the probability of an electron at a point, say, right there. Okay? And that would only tell me the probability of finding the electron at that point. If we want to know the probability of finding an electron at a particular distance from the nucleus, we'd have to add up all the points on the surface in order to determine that. So, for example, if we had a spherical shape like an s orbital, what we want to do is multiply the wave function, the total wave function, by the surface area of the sphere, which would be 4 pi r squared, get the probability of finding the electron at a particular distance from the nucleus. Now let me reiterate that. If we just square the radial component of the wave function, if we square that wave function, we're going to get the probability of finding it at a particular point at a distance from the nucleus. If I wanted to know what the total probability, where we add up all the points on the surface, if I wanted that total probability of finding the electron at a distance, then I have to take into account the surface area of the sphere. And to do that, what we have is something called the radial distribution function. If you heard that shaking in the background, that was my dog Jeffrey just shaking as he is wont to do. So here is the radial distribution function. Basically what we do in the radial distribution function is we just take the radial component of the wave function and we square that, which is what we do to find the probability at a particular point, but then we multiply that by r squared. And the multiplication by r squared actually allows us to calculate the probability at a particular distance from the nucleus. All right. So here's our radial distribution function. And of course we'll note if r is equal to 0, then the radial distribution function is going to be equal to 0. So when we consider that radial component and the radial distribution function, we'll find that we actually have 0 probability of finding the electron at a distance 0 from the nucleus. Okay, so here is a plot of the radial distribution function for the different orbitals of the hydrogen atom. We'll notice, for example, if we look at the 1s orbital here, all right, that now for the 1s orbital there's actually 0 probability finding the electron at the nucleus we indicated, and there is a maximum at a specific distance from the nucleus. Okay. Now in class we'll actually show how we can calculate what that distance is from the nucleus using MathCAD. If we look at these different orbitals, we'll see that of course all of them have 0 probability at the nucleus, and several of them have multiple maxima. Looking at, for example, the 2s and the 2p orbitals, if we look at the 2s and the 2p orbitals here, we'll see that the maximum for the 2p orbital is here. The maximum for the 2s orbital is here. You'll notice the maximum for the 2s orbital is actually farther from the nucleus than the 2p orbital, which again may seem counterintuitive based on what you had learned in general chemistry about the relative energies of the 2s and the 2p orbital. And again, we'll be talking about that in more detail in a future video. But we'll also note for the 2s orbital that it has more than one maximum. You may remember, of course, the 2s orbital has a node, which is right here, but it also has another maximum which is closer to the nucleus. Okay, so you can see that the maximum out here is a global maximum, but we also have another maximum. And when we start dealing with multi-electron systems and electron repulsion, that's going to have an impact on the energies of these orbitals. We also can see here the maxima associated with the 3d, 3p, and 3s orbitals. And we'll note again the 3s here is farther from the nucleus than the 3p, which is farther from the nucleus than the 3d. Again, somewhat counterintuitive, but again, you'll notice that the 3s has several maxima. It actually has 3. For the 3s orbital, there's a maximum here, there's a maximum here, and there's a maximum here. For the 3d orbital, there's only one maximum here. So these different behaviors are actually important when we start talking about multi-electron systems and using the orbital approximation, and actually start asking questions about electron penetration when we look at the properties of these systems and the wave functions, and what the wave function will tell us about the specific details and properties of the electrons in these one-electron systems. So this ends our discussion of the wave function associated with the hydrogen atom and one-electron systems in general. In our next set of videos, we'll begin to look at the behavior of atomic systems which have more than one electron. Aren't we looking forward to that? So stay tuned.